Today, stop talking, please. Stop talking, please. Back corner, who is still talking while I'm asking you over and over to stop talking. How many times should I have to repeat myself when I ask something like that? None is the answer. How many times did I repeat myself? Five. Let's not make a habit out of this, okay? Today, we're going to we're going to finish Chapter 5, looking at Section 5.2. What we're doing here in Section 5.2 is an extension on the ideas that we covered in Chapter 4. So we're going to start by just kind of rehashing a little bit of that, and then kind of extending that out, okay? So in Chapter 4, we asked you guys to do things like find the exact value of sine inverse of 1/2 without using a calculator. When you hear exact value in trig class, what are we expecting you to use? Unit circle, yeah. So remember, for sine inverse, the range for sine inverse was -pi/2 to +pi/2, which means that we're looking in quadrants 1 and 4 for where y is equal to 1/2. So I'll go to the unit circle and see what I find here. So over here on the unit circle in quadrants 1 and 4, I'm looking for where y is 1/2. That happens at pi/6. So that's my answer. Everybody feel okay there? Remember doing that? And then we said, okay, what if we give you, instead of just asking you to evaluate sine inverse of something, what if we give you an equation to solve, but in doing so, we also would provide like a range of values to solve over. So again, what we do is we'd start by figuring out what quadrants are covered from pi/2 to 3pi/2. That'd be quadrants 2 and 3. So we're going to then go to the unit circle and look at where y is 1/2 in quadrants 2 and 3. So if I look, check all my y's in there, that's the only one that works. So my answer should be 5pi/6. So that's like the things that we would have done in Chapter 4, right? That all look familiar? Okay. What we'll do now in Chapter 5, in this Section 5.2, is kind of extend on those ideas. So before, we'd ask you to find like sine inverse of something, where the range you're using as the fundamental range for the function kind of included. Or if we asked you to solve for the equation, we'd give you a range of values to solve over. What if we don't give you a range of values to solve over? How many answers are we going to have here? More than 2. Infinity is the right answer. Why infinity? Okay, but why is getting rid of the range going to create infinitely many solutions? Great. So as long as I have a solution, any angle coterminal to that solution will also be a solution, right? And because there's infinitely many angles coterminal to a given angle, that's going to give us our infinitely many solutions, right? So from our first example, we know that pi over 6 is a solution, right? And from our second example, we know that 5 pi over 6 is a solution. Are those two angles coterminal to one another? No. How do I know that? How am I checking? Great. The difference between them is not 2 pi. They're not 360 degrees apart. I use 2 pi because these are both radian measures, but that's the right idea. Everybody's okay? If I subtract them, I get 4 pi over 6 or negative 4 pi over 6. Either way, it's not a multiple of 2 pi. So these answers are unique, right? One is just not coterminal of the other. But we need a way to write pi over 6 and then everything coterminal to it. Or how to write 5 pi over 6 and everything coterminal to it. We could write in words, but we're not going to do that. We're going to use mathematical symbols to do that. So the way that we write and everything coterminal is we're going to write plus 2 pi k, where k is an integer. So that stuff at the end just means that angle and everything coterminal to it. Just a symbolic way to say that same information. Is everybody okay with that? Okay. Sure. Okay. So that's what we do if we're not given an interval. What if we start giving you intervals that seem bigger than usual? Remember in chapter 4, the interval that we gave you was never bigger than pi, like 180 degrees, like half of the unit circle. Here we're going to start giving you bigger intervals that might be the entire unit circle, might be 2 pi big, or it might be even bigger than that. Maybe like 3 pi or 4 pi or 7 pi or 27 halves of pi or something. Like could be as big or small as I wanted. And we want to find all the answers over that interval. Well, we'll start the same way. So we'll go to the unit circle. We'll look for where y is equal to 1/2. But this time I'm looking over the entire unit circle, right? Because my interval I'm solving for is 0 to 2 pi. So let's see, I have here is a place where y is 1/2. Keeps squiggling through. There's the other place where y is 1/2. And I keep looking. So those are both my solutions. Everybody cool? So we're going to be getting more than one solution now. Now, the other way that I can think about that is if I take my infinite solution way, and what if I just fill in a value for k, right? These infinite solutions can generate as many answers as I want by just plugging in a value for k. So what if I plug in 0 for k? So that just gives me pi over 6, which is in between 0 and 2 pi. And if I take the other general solution, again, plug in 0, that's just going to give me 5 pi over 6, which is also in between 0 and 2 pi. So I can use that general solution to get the same thing I would get from the unit circle, right? By just picking values of k. It'll output answers, and then I can just check if those answers lie in the given interval that I'm looking at. So in a way, that general solution is like my skeleton key. It'll generate any answer I want. I just have to keep plugging in k's until I find the ones that I want. Does that feel okay? All right. So we've extended this idea from chapter 4 by looking at situations where we can have infinitely many solutions. We've looked at situations where we can have more than one solution. The other extension that we're going to make is ones where we have to do some algebraic manipulation before we're able to go to the unit circle. So let's take a look at this one. It says cosine squared x is equal to 1. Now, before I'm able to go to the unit circle, the trig function on my left-hand side has to be a single trig function, and that's it. No coefficients, nothing added or subtracted to it, no exponents, just a sine, cosine, tangent, secant, cosecant, cotangent, right? So all I can have on the left-hand side. If I take a look at this guy, do I have that? No, we have a squared. So I have to get rid of the squared. How can I do that? So we can square root both sides. What do I have to remember when I square root both sides of an equation? Yes. So the square root of 1 is 1, but because we did the square root to both sides, got to have that plus or minus there also. Everybody feel okay? All right. Now, there's no plus or minus 1 on the unit circle. So what I really need to think about this as is cosine x equals 1, and then cosine x equals negative 1. And then I can go to the unit circle and look for where x is 1, and then go to the unit circle and look where x is negative 1. So let's start with x is 1 first. So here's one answer. Keep looking at my x's. Negative, oh, that's not what I want right now. I'm just looking at positive 1. And if I go around again, I'm at 2 pi now, right? Is 2 pi an acceptable answer for me to give?
No.
Let's look. Well, it says 0 to 2 pi. Does the parenthesis mean that I can count it or not? The parenthesis means it's not included in the solutions. The bracket means it is. So my only answer here should be 0 from this piece. And then if I go and look at the other one, I go to the unit circle and look where x is negative 1. We'll do the same thing. So check my x's. There's 1. And then keep checking. That's the only one. So that's at pi is my other solution. Everybody so far so good? No big deal, right? Let's take a look at the next one. So here we have 3 tan squared x equals 1. And again, we're solving from 0 to 2 pi. What's wrong with this one? Good, I have an exponent and a coefficient. Which one should I get rid of first? The coefficient, that is correct. When we're solving, you follow the reverse order of operations. So you undo adding and subtracting, and then multiplying, dividing, and then exponents. So it's the opposite of simplification. So we'll divide both sides by 3. Then we'll square root both sides. What do I have to remember when I square root both sides of an equation? Plus or minus. Now, when I go to the unit circle, I remember that tangent is y over x, right? So I don't love the way that my answer is currently written as plus minus square root 1/3. Oops, it's supposed to be a 3. Sorry about that. So I'm going to monkey around with that until I get into a form where it's a little easier to see what x and y I should be looking for. So I remember that the square root of a fraction is the same thing as the square root of the top over the square root of the bottom. And the square root of 1 is just 1. So, okay, now this looks okay. So I'm going to look for where y is 1 and x is square root 3. If I go to my unit circle, well, I see a spot where x is square root 3 over 2 and y is 1 over 2. Now that's not exactly what I have, but I can make it what I have, right? So I'll just come back here and multiply the top and bottom by 1/2. So what I'm going to be looking for is where x is plus or minus the square root of 3 over 2, and where y is plus or minus 1/2. Is everybody okay with that?
Why'd you multiply by 1/2?
So that it would match the stuff that I find on the unit circle.
Can you go back to the unit circle?
Yup. So I saw in the unit circle, I saw a spot where x is square root 3 over 2 and y is 1 over 2. So I saw what I kind of needed, but I didn't have it over 2 in my answer, right? So to make it that way, I just multiplied the top and bottom by 1/2. So I could make the fraction be the y over x that I saw in the unit circle. All right, so let's go through and find all the places that we're looking for. So here's one where x is square root 3 over 2 and y is 1/2, and they could either be positive or negative. There's another one. There's another one. And there's another one. So my 4 answers are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Is that okay? Again, plus or minus is okay. And again, I know I only have to look at the unit circle here because the interval I'm solving over is just 0 to 2 pi. It's the unit circle, right? All right, let's take a look at the next one here. Whoa there, Mr. Kulak. What the heck is going on with this one? We haven't seen one like this. This has 2 trig functions in it. I have 2 cosine squared plus cosine x equals 1. The heck am I supposed to do with that? Well, when you look at this, does this remind you a little bit of an equation from Algebra 2? What kind of an equation does this sort of look like? Nope. Although you're on the right track. You're in the ballpark, you're just playing the wrong game. More general than that. I'm looking for a word. It's not a slope-intercept equation. What's the exponent? What's the exponent? 2. What type of equations have a degree 2 like that? Starts with a Q. Quadratics. Is that what you said? I'm sorry, it sounded like a pajamas or something. I was like, I'm not even sure what you said there. Yeah, this kind of looks like a quadratic. You're like, Mr. Kulik, I don't see it. Well, imagine this. Let's imagine we just replace our cosines with y's. Now it definitely is quadratic, right? Where I have a squared term, a linear term, and a constant. Everybody agree? Okay. From your Algebra 2 class last year, what were some of the different ways you used to, or methods we used to solve a quadratic? You could use the quadratic formula. What else? What? Completing the square. Yes, that's probably what you are thinking of. Yes, good. What else? There's several more that I know you would have done. Factoring is another. Excellent. What else? 2 more that I have in mind. One of which we've already used. Not the Pythagorean theorem. How'd we solve the previous one? No. Yeah, so we can just, sometimes we can just use a radical, right? That was quadratic. It was tan squared. And then the other one that you probably talked about was graphing. Regardless of the type of equation you have, you can always solve by graphing, particularly if you have a graphing calculator. It makes it relatively easy to do so. So of these, which ones are the most, well, let's look at the ones we can't use, right? If I have a linear term with my quadratic, radicals out. Can't do that. Which ones are, or which one is like the most tedious? Okay, if you don't have a graphing calculator, that's certainly not a whole lot of fun. Algebraically, which one's the most tedious? Completing the square. That's the one where you had to add like b over 2a squared to both sides and then do some factoring. If there's a leading coefficient, it's like kind of weird. So you don't want to do that. So it really comes down to this between factoring and quadratic formula. Let's say we do the quadratic formula, yeah? What are the initial conditions I need to have to use the quadratic formula? If what? So if ax squared plus bx plus c is equal to 0, then x is equal to negative b plus or minus square root b squared minus 4ac all over 2 times a, right? That's the statement for the quadratic formula. So when I said the initial condition, this is what I'm talking about. Do I have that in our problem? No. What's wrong with what we have? Right, it doesn't equal 0. Can we fix that? Yes. How would we fix it? How about we just subtract 1 from both sides so it's equal to 0, right? I think that's what you're trying to get to, but vocabulary escaped you. Is that okay? All right. So now we're all set. What's the value for A? 2. What's the value for B? 1. And what's our value for C? Negative 1. Okay, so we can say x equals negative 1 plus or minus square root 1 squared minus 4 times 2 times negative 1 all over 2 times 2. Yeah. 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 All right. What's 1 squared?
1.
Okay. What's 4 times 2 times negative 1? Negative 8. What's 2 times 2? What's 1 minus negative 8? Nope. Not negative 10, not negative 9, not negative 8. 1 minus negative 8. 9.
I thought it was 1.
Okay. What's the square root of 9? 3. How do I do negative 1 plus or minus 3? Is that plus or minus 2? No! How do I do that? You split it, right? You do negative 1 plus 3 as one problem, and then negative 1 minus 3 as another problem. Everybody okay so far? All right. So we have then y equals 1 or y equals negative 1, and we're done, right? No, why not? What is our original problem?
Wait, can you go back a little bit?
I will in a second. What's our original problem? Does it have any y's in it? No. What variable's in our original? X's, right? So we got to put our x's back. Remember we said that y was cosine x? So we got to go back here and replace these y's with cosine x. Right? Now we can go to the unit circle. So we're looking for where x is 1/2. So let's go check that out on the old UC there. Let's see. So I got here pi over 3, chugga, 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 and 5 pi over 3. And then for x equals negative, or cosine x equals -1, I need to go to the unit circle and look where x is equal to -1. So we'll go back. Because it's cosine. So that's the only spot there. So my answer is just pi.
Make the original part x and 1.
You can call them whatever you want, but those need to be your three answers. Whatever you want to name your variables is okay. So far, so good. All right, let's look at, I think I got two more examples and I'm out of here. If I look at the next one, all values of x, what's that going to mean? We're going to have to put that plus everything coterminal to it on every answer we get, right? And then if I look at the other thing, I see this and I go, oh no. What do you see here that's different than anything we've seen to this point? Yeah, I have different trig functions. I've seen just sine, I've seen just cosine, I've seen just tangent, I've seen cosine squared and cosine. I haven't seen tan and sine or something like two different things rattling around together in the same problem yet. Rutro raggy. That's a Scooby-Doo joke. Okay. So, two options here on a problem where I have different trig functions in it is I can try to use an identity to make them all the same kind of trig function. So maybe I can look, is there a way I can change tangent into just sines?
Yes.
No. I can turn tangent into sine over cosine, but that doesn't help me because I'll still have two different trigs in it. I can turn into secant over cosecant. That doesn't help me at all. 1 over cotangent. That doesn't help me at all. Can't do that, right? I can't get just sines. Can I change sine into just a tangent? No, right? I can turn sine into 1 over cosecant, but that doesn't help me. All right, so an identity is not going to help here. Instead, what I'm going to try to do is I'm going to try to get everything onto one side and do some factoring. So I'm going to subtract the tan x to the other side. And now I'm going to try to factor this. Do you see any squareds anywhere on here? No. So is it quadratic? No. So it's not going to factor like a quadratic. Everybody's good? It's going to factor easier than that. So easy that it's going to go back to like a pre-algebra type of factoring that you've all forgotten. We're just going to be looking for a least common multiple. So if I look at my first term and I look at my second term, do you see anything in common between them? They both have a tangent. That's my least common multiple. I'm going to factor that off. When I factor tangent off of the first term, what was left? You're going to have 2 sine x, right? Remember, when you're factoring, you're really doing division. What do I get when I factor tangent out of the second term. I get 1, right? I get 1. I factored, like if I had, 2xy minus x, I can just like factor an x off, right? It's the exact same thing. Instead of x's and y's, I have sines and tangents. Sure. Yeah? You see it now? Now notice in our 2 factors, 1 factor, 2 factor, how many trig functions are in each of our factors? Just 1. That's great. So now I'll apply the zero product property. And in each equation that I write, I have only 1 trig function in it to solve. And I can do that now. So far, so good? So if I look at the first equation, tan x equals 0, the trig function is by itself, so I'm ready to go to the unit circle. I'm looking for where y over x is equal to 0. That means I'm looking for where y is 0 and x is not. So let's go to the unit circle and check that out. So y is 0, x is not. Chugga, 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 chugga. Chugga, 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 chugga. Y is 0, x is not. Chugga, 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 chugga. And that's it. So 0 and pi. I need a little bit more space here. Can we cooperate at all? So I'll say 0 and everything coterminal, or pi and everything coterminal. Ugh, come on there, Kulik. All right. Now look at the second equation, 2 sine x minus 1 equal to 0. Is that ready to go to the unit circle? No. Why not? Yeah, because I don't have the 1 trig function by itself. So what do I need to do first? Add 1 to both sides. Very good. And then we can divide by 2. So we'll go to the unit circle and look for where y is 1/2. So go back up to my unit circle. Look for where my y is 1/2. So that's one spot. There's another spot. Keep checking my y's. That's all the spots. So pi over 6 and 5 pi over 6. Okay. Got one more thing to point out to you. So those are my answers. The way this is written is correct. It's fine. I'd give you full credit for this on a quiz or a test or whatever. However, that's not how it's going to be written in the back of the book. Let's think about what that piece in green that I've circled, what answers are there? If I look at the first solution, that's saying that like things like 0, 2 pi, 4 pi, 6 pi, 8 pi, etc. are all solutions, right? If I look at the second thing, it's saying that answers like pi, 3 pi, 5 pi, 7 pi, etc. are all solutions. If I look at that group of answers together, that means that 0 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, all solutions, correct? The more compact way of writing that would be just like that. That's how it's going to look on the answer key. Do you have to write it that way? No. I'm just pointing this out to you in case you're looking at the answers in the book and go, that's not what I wrote, but I think I did that right. Just, like enumerate some solutions and make sure that what you're getting and what this answer is getting a match up. As long as they're the same set of answers, it's fine. You don't have to write it that same way. Does that feel okay? So again, just pointing this out to you that in the back of the book, we're going to write as compactly as possible. Because if you got to type this thing out, less symbols is easier. But you don't need to do that for me to have a correct answer. Right is right, whether you write it long or short. Doesn't make any difference to me. Correct is correct. You know what I'm saying? All right, last example. Find all values of x on the interval from negative 4 pi to 2 pi. Yeah. Sure. Notice right away here, this is the biggest interval we've tried to look on, right? This is like 6 pi long, this interval. So we're potentially looking at a lot of possible answers here. Because that's bigger than 2 pi, or it doesn't include 0 to 2 pi, I'm going to write my answers as infinite answers. And then I'm going to use that to generate the answers that I actually need. So let's look at my problem. I have sine squared x is equal to sine x. I notice this is a quadratic equation. How do I know it's quadratic? You see the squared on there. However, I also notice that this is different than this quadratic one we looked at up here. Because the one that I'm trying to solve right now doesn't have a constant term, right? 2 cosine squared plus cosine equals 1 has a constant term, has that 1 in there. What I'm trying to solve doesn't. Just sine squared x equals sine x. Does that make it harder or easier? Makes it easier not having the constant term there. Okay? Makes it easier. Why does it make it easier? Because now I can just factor using a least common multiple. So I'll just subtract the sine x over. And then we'll factor a least common multiple. What's the thing in common between sine squared x and sine x? Sine x, right? When I factor sine x out of sine squared x, what does that become? Becomes sine x, right? When I factor sine x out of sine x, it becomes 1. Right? And you could check by just kind of like distributing things back through and making sure you get what you started with, right? Should be relatively easy to do that in your head. Okay. Apply my zero product property. The first equation is all set. I'm going to go to the unit circle and just look for where y is 0. So let's go check that out. So let's see, y is 0 here at 0, checking my y's. There again at pi, checking my y's. Those are the only ones. But because my interval is bigger than 0 to 2 pi, I'm going to use the infinite solution here. And use that to generate my answers. So I'll start with k equals 0. So that gives me 0. That's in between negative 4 pi to 2 pi. And I have pi plus 2 pi times 0. That's pi. That's also in between negative 4 pi to 2 pi. Everybody's cool so far? Since those both work, let's get bigger. So if I say k equals 1, I'm going to have 0 plus 2 pi times 1. That's 2 pi. Ooh, that's right on the border. Does the bracket mean keep or throw out? Keep. Good. And then I have pi plus 2 pi times 1. That's 3 pi. And that's too big now, right? Everybody see that? So that tells me, since I found one that was either like right at the tippy top of my interval or too big, tells me I've gone as big of the k as I need. So now I need to look at smaller k's. So let's try k equals negative 1. That's going to give me negative 2 pi. That's okay. That's in there. And it gets me negative pi. That's a keeper. That's in there. Right? Still in between negative 4 pi and 2 pi. All right. Well, let's do another negative now. So negative 2 for k. So that's going to be negative 4 pi. That's right on the border, right? Is that a keeper, though? Yes. Why is it a keeper? Because of the bracket. And then I still need to do the other one for k equals negative 2. So that's going to give me negative 3. And that's in between. And I know I'm done here because I found the one that was like either too big or right at the very biggest I can have. So I found all my answers here. So I'll say x equals negative 4 pi, negative 3 pi, negative 2 pi, negative pi, 0, pi, and 2 pi. Is everybody good with how I knew to stop? Tia?
How it says k above the answer 0?
It says k equals 0.
Does it say 0?
That's what it says. Is that what you're asking?
Yeah.
Okay. All right. But we're not done with this yet, unfortunately, because we still have another side or another half to do. So we'll add 1 to both sides. We'll go to the unit circle and look for where y is equal to 1. So looking for y's. Oops, there's 1 at pi over 2. That's the only y. That's 1. Oh, thank goodness, Mr. Kulik. So we can say x equals pi over 2, but we're going to write that as an infinite solution. And then just like before, we're going to enumerate through some values of k to find our solutions that work. So I'll start with k equals 0. That fits. And so it's still that, since that still works, let's go and make it 1 bigger. Let's make k equal 1. Now, pi over 2 plus 2 pi, to add those together, I have to have a common denominator, right? I'm not going to make a common denominator. I'm not going to show the work for it. I'm just going to do it in my head. Is everybody okay? So when in a minute, when somebody asks me where this 5 over 2 pi comes from, I'm going to smash my head into the desk and like cry a little bit, okay? Don't do it. So I get 5 over 2 pi, or 2.5 pi. Guess what that is? It's too big, right? We're going from -4 pi to 2 pi. So we're done going up on k's. Let's go down now. So we'll do -1 for k. Again, make my common denominator. That's -1.5 pi. That's good. That one works. We'll make it smaller again. That's -7 pi over 2. That's -3.5 pi. That one will work. But when I subtract another 2 pi from this, it's definitely going to be too small, right? So those will be my other 3 answers. So I'm done. Now, I wrote out all this mumbo jumbo, right? I did this just to illustrate to you what I'm doing. In practice, I would not write all this stuff down and show all this work. All I would have done in practice is I would take 0 and I'd add 2 pi to it until I found something that was bigger than 2 pi. Everything that was still smaller than 2 pi I would keep, right? And I would subtract 2 pi from 0. And until I got something smaller than -4 pi. Everything that was in between, I'd keep. Right? I'm not actually going to write anything down. I'm just going to do it in my head or on my calculator or just like write down on a sheet of paper just with commas after each other. I'm not going to write k equals and do all the computation because I don't really have to. Right? All I'm really doing is adding and subtracting 2 pi to these unit circle answers. And just keep keeping the answers that fit inside the interval that I'm looking at. Is that okay with everybody? In practice, I wouldn't write all this down, although you are free to do so if it helps you understand what's going on. I wrote it down this time so you can see what's happening and understand a little bit better what I'm doing. In practice, though, it's really inefficient, takes up a lot of space, and takes a lot of time. Aaron.
How do you know when you have to like add and subtract 2 pi versus like you just like leave it as a what you found?
Well, like what we did for the
Mhm.
example before.
So if I look at the interval here, it's more than the unit circle, right? As opposed to this question here, where the interval is just the unit circle. That's how I know. If it's asking for just the unit circle, all I do is pull them from the unit circle and I stop. If it's bigger than the unit circle, well, I have to consider that answer and then anything coterminal to it that still fits inside the range of values. Is that?
Yeah.
Sure. Okay. Tia, you had your hand too. What did you have?
So if I don't want to do all that practice, I would just take the x equals 0 and multiply it by 2.
No, adding and subtracting. And just checking to see if the no, as long as you're getting answers inside this range. So as soon as you stop, you can stop adding, then you just start subtracting. As soon as you get something too small, you stop and then go to the next answer and do the same thing with your next answer, just adding and subtracting 2 pi's until you find something that doesn't land in the range, and then you do the other direction. Stop when you find something that doesn't fit in the range, and go to the next answer. And you just do that over and over again. Ashton. Yep. All right. For your guys' homework on this, I need you guys to do for me, let's say 15 to 33, and then 43 to 46. Now, keep in mind here that each one of these problems is really 4 problems because there's 4 different intervals I want you to solve over. Now, I tried to be nice in how I picked these intervals, right? Because if you solve from 0 to 2 pi, automatically you can get the infinite answers because all you have to do is slap the 2 pi plus 2 pi k at the end of it, right? Here, from 0 to 2 pi, you've already done in part A. So all you need to do is check 2 pi and then from negative 2 pi to 0. So you only have to enumerate a few answers more because you have half of it done, right? And then on this one, you've already done from negative pi to 2 pi in the previous question. So you just take all the answers from the previous question that land there. And then all you have to check is from 2 pi to 4 pi for more answers. So I tried very hard to give you problems that, like, the previous problem already did part of it for you. So you don't have to, like, enumerate a million trillion of these things. Does that feel okay? Okay. So that's it for chapter 5. Next time we're gonna have our review day. So your half sheet will be due next class. I want to show you guys though the test format. I wrote down the test format on the review pack because it's unusual compared to other tests. So your chapter 5 test format, there's 10 total questions. You're only going to do 8 of them. The first 4 questions are required questions. You must do these first 4. 2 of them are simplifying, just like we did on the homework quiz or the first couple of homeworks. The second 2 are solving, just like we just did. The next 6 are trig identity proofs. You need to pick 4 out of those 6 to do. Any 4 is fine. So if you have one where it's just like, I don't know what the heck to do with this, it gives you the ability to skip. Because sometimes you look at them and you know what to do, and sometimes you don't, right? So this gives you a little bit of leeway in terms of, I can stay away from the things that's like, I don't know what to do with this. Or just like, I don't have any good ideas right now. you can avoid that, right? You still have to do some, but it gives you some freedom there to choose. So keep in mind the test format as you're writing your note sheet. You will not need to include any identities on your notes. I will give you the identity sheet that I printed for you. That'll be the identity sheet I give you on the test. You do not need to memorize those. You do not need to put it on your note sheet. The thing that I printed to you will be what I hand you on the test. The unit circle on back, it's going to be the same sheet. Cool? Okay, any questions about test format stuff? Okay, I'm going to stop talking now. You guys can take the next 20 minutes or so remaining in class to work on your homeworks or whatever. Cool? Questions?